Hi everyone, welcome back. I know we've done several videos on drawing resonance forms. So in this particular video, what we're going to do is I'm going to solve some examples for you so that we can see how these problems should be attempted. You know, what should be the approach when you're trying to draw significant resonance forms for a given structure. And when possible, we'll also try to draw a resonance hybrid for these. Okay, so let's start off. And I've picked some problems from homework examples. That's what I'm doing here. So all of these problems are from the homework. So let's say we have a structure where this is the molecule. Okay, so that's the given structure. And so whenever you get a molecule, you know, you get a structure to do resonance on. Uh, I think what you want to do is first assess the structure itself, because you have to ask yourselves a very important question. And that question is, where do I start? What's the first electron push that I'm going to do? And to basically arrive at that decision, you'll have to evaluate your structure to find some scenarios, like a scenario that you can identify with some of the basic scenarios that we've already dealt with. So let's say if we look at this structure, when I look at it, what I notice is, okay, there's a positive charge on a carbon. So there's a carbocation here. Okay, a positive charge in the structure. There is a double bond in the structure. There is an oxygen with some lone pairs. Okay. Now, if we look at it closely, you know, and start evaluating it, what you notice is that this positive charge is at an allylic position because it is connected to a vinylic carbon. Similarly, the oxygen with its lone pairs is on an allylic position also. And so that sort of gives us clues as to what could be like the first electron push. Now we've identified two scenarios here. And so you could pick either one. It doesn't matter where you start. You could pick either scenario. And so in one of the earlier examples that was similar to this, I actually started by pushing the pi bond here to get rid of that positive or move the positive charge. So what I'm going to do in this example here is actually start from the lone pair. So what I have here is a lone pair at an allylic position, because this is a vinylic carbon, so that's an allylic position. So when you have a lone pair on an allylic position, the first electron push that you do is to start with the lone pair and you push it down. Okay, you push it down, but this is also the scenario in which if you just leave it at one electron push or one push of electrons, you exceed the octet on this carbon. So to relieve that situation, what I'm going to do is I'm going to simultaneously push that pi bond over to the next carbon, the other vinylic carbon in some sense. Okay, so the lone pair is pushed to the space between the allylic atom and the vinylic carbon that it's connected to. And the double bond itself is pushed over to the other allylic atom. So once I've done that, I can stop here and I can draw the resulting resonance form. So I'll have that. The positive charge is still here, didn't go anywhere. Now, this carbon here should have a lone pair on it, which will give it a negative charge. And there should be a single bond between these two carbons now. The double bond became a single bond. And there should be a double bond between this carbon, which was vinylic before, and the oxygen atom. And the oxygen atom has another CH3 group connected to it. The oxygen had two lone pairs. It used one of those. So now it is left with one lone pair. Okay. And since the oxygen has three bonds around it and only one lone pair, what that means is this oxygen is also positively charged. If you're not comfortable with this, like I always say, go ahead, do the formal charge calculations, okay? So only when you're comfortable, start just qualitatively, like quickly evaluating it and then putting down formal charge. So this is where we are right now. Okay, that's the new structure that we got. Now, so these are both resonance forms of each other, okay? Now, we started pushing electrons from this direction, from the right-hand side. So we will keep pushing in the same direction, from right to left. That is what we're going to do. Now, if you look at the second structure now, so we came from here, you know, so this double bond and everything is a result of the electron push that we did. And we basically stopped at this carbon, getting the lone pair. So that's where we are now. Now, if you look at this scenario here, what we have is a lone pair adjacent to a carbon with a positive charge. So that's another scenario that we've seen. So in this scenario, what we're going to do is we're going to take the lone pair and push it to the space between the two atoms, okay? Take the lone pair, push it to the space between the two atoms. That's going to give us the next resonance form where we have this, and now there should be a double bond. So we've put a double bond over there. Then a single bond, double bond to the oxygen, another carbon, one lone pair, positive charge on that oxygen. We didn't do anything here, so all of that basically gets transferred over. And this end, if you look at it, we had a positively charged carbon, we had a negatively charged carbon, those combined, and so no charge at this point. Okay, and if you look at your first structure, compare this first structure to the last structure, what you notice is the charge is basically preserved. You started with one positively charged and you end with one positive charge. I think that's something that you can keep track of. Okay, so if you have only one charge, then you must definitely have at least one charge throughout all your resonance forms. Okay. But if you have two charges, then they could basically combine and then kill the charge at some point. Again, shortcuts, not shortcuts, but I think some things that you have to identify as you practice, okay? But I think at this point we are done. These are all the resonance forms that we can done. So these are 3 resonance forms for this given structure. And now what we can do is we can evaluate these resonance structures to predict which one is the major contributor. So first structure, we have a positive charge on a carbon, which means incomplete octet. So whenever you see that, basically build it into your head, incomplete octet. Positive charge on a carbon, incomplete octet. Positive charge on oxygen, but is the octet incomplete? If you look at the oxygen, it has 1, 2, 3 bonds and a lone pair, that's 8 electrons. That means the octet's still complete. So that means this is a structure where all octets are complete. So this is going to be our major resonance form, okay? Now, if you look in terms of charge, I would say this is the least contributing resonance form because it has too many formal charges, okay? The first structure and the third structure have the same number of formal charge, 1 formal charge and 1 formal charge, but the third structure has all octets, all atoms with complete octets. So that is our major contributing structure here, okay? Now, based on this again, if we look at all of these, we can also try to draw the resonance hybrid, okay? Which should be a summation of all of these. So what is preserved between all 3 structures here is this skeleton. And if you look throughout, the oxygen has at least 1 lone pair in all the structures. I'm going to include that 1 lone pair, okay? And then between all the structures, if you look, there's a single bond here, but a double bond there. That means this is a dash bond, double bond, single bond, single bond. That's a dash bond, single bond, double bond, double bond. That's also a dash bond. So that's where the electron density. So these dots, when we have these continuous dots, that basically means that the electron density is spread out, delocalized over those atoms, okay? And then we can put the charges, the partial charges. If you look, the oxygen has positive charges on 2 of these structures. So that means the oxygen has a partial positive nature here. This carbon has del positive. So this is also del positive. And then we have one structure where this carbon is del negative. So it is a del negative over there. So that would be the resonance hybrid for this structure, okay? So that's our resonance hybrid, which captures the electron distribution in all of the contributing resonance forms, okay? So that's the first example. Let's look at another example where you're going to draw something similar. Okay, so let's start with this structure here, and we're going to draw resonance forms, all significant resonance forms for this molecule or for this given structure. So again, we start by analyzing the structure to identify a criteria, okay, a scenario where we can actually start, something that would tell us that, okay, this is going to be the first push. So when you look at this structure and maybe like, you know, think about all the scenarios that we talked about, notice that this has 2 atoms with a double bond, and where one atom is more electronegative than the other atom. So we have a carbon-oxygen double bond here. So that was the first scenario that we talked about. So that may be a good point to start. Okay, so let's start here. And in that scenario, what we do is we take the pi bond and push it over to the more electronegative element. So the first resonance form that we will get will now have a single bond between that carbon and oxygen. The oxygen has 3 lone pairs, and so it has a negative charge, and the carbon here has a positive charge. Okay, so that would be our resulting resonance form. But can we do more is the question. And so do not stop. Definitely like keep evaluating your structure to see if there's more that can be done. Okay, now again, since we started from there, we will not go back, do more over there. Now we have to start extending into the other side. Okay, so if you look at this positive charge, I would say that it's an allylic positive charge because that carbon is connected to a vinylic carbon. So it's a positive charge at an allylic position. And since that's true, what I can do is I can take this pi bond and I can move it over. That's how you push electrons when you have a positive charge at an allylic position. And then we'll go ahead, write what we get. So now we have a double bond over here. Oxygen with 3 lone pairs, negative charge there. And since we used this pi bond and we moved it to the space between those 2 carbons, this carbon is now going to have a partial positive charge. And as you can see now, this is again a positive charge at an allylic position. So what we can do is move this over, the pi bond over, would give us another resonance form. If this double bond stays, that double bond now moved. This double bond is still here. Oxygen still has 3 lone pairs, negative charge, and the positive charge should now be on this carbon. So notice how we are moving in one direction, okay? That is important because if you go back, you're going to generate some of the previous resonance forms. Okay, this positive charge is again allylic. So move that pi bond over. Yes, and you might be wondering that, yes, it's a ton of resonance forms. Yes, it's possible, but resonance explains stability, you know, so the more resonance forms a molecule has, the more stable the molecule is. So double bond now here, double bond here, double bond over here, oxygen, negative charge there. And the positive charge is now on that carbon. Okay, now is this positive charge still allylic? Can we move forward? So if you look at it, we haven't really engaged that side yet, but this is a vinylic carbon and that's a positive charge. So we can actually use that double bond, because from that double bond earlier, we went down. So now we're coming back up. So we can use the pi bond from here, move it, and double bond here. Now this becomes a single bond, oxygen, negative charge, positive charge on this carbon. So is that it? Did we finish? Do we have this resonance for, did we see this resonance form before? Like, have we come back like full circle? Well, actually, no, because if you compare this resonance form to that resonance form, what you notice is the position of the double bonds within the ring is not the same. So it's not the same structure. So from here, what we can do is, now we have a carbon with a positive charge with lone pairs next to it, or we have a lone pair adjacent to a carbon with a positive charge. So we can push one of these lone pairs down, and that is going to bring us to a structure where we have double bond between the oxygen and that carbon, two lone pairs on that oxygen, and the double bond in this positions. So you notice we almost came back to the same structure. In fact, these two are the same molecules because these are resonance forms, okay? So resonance forms are not two different molecules. So hopefully you remember that also from the introductory video. They're not separate molecules. They're different representations of the same molecule. The only thing that's different is the electron distribution between them. So that's what's different between these two structures, but they are not, I mean, when you look at it, the Lewis structure, they're not alike, you know? So these are all the resonance forms. So we can go ahead and put the resonance arrows here. Okay, and so that's all the resonance forms that are possible for these structures. And now if you evaluate these structures, you would notice that this first structure and the last structure are the ones where we have complete octet for all the atoms involved, because for every other resonance form, there's a positive charge somewhere, and that carbon is missing. There's a carbon with a positive charge, and that carbon is missing its octet. So it's in complete octet. So these two are have complete octets for all the atoms. Additionally, notice how these do not have any formal charges. Every other resonance form has two formal charges on atoms. So that means these two are the major resonance forms, okay? And since these are the major resonance forms, you can actually draw a resonance hybrid, okay? So the resonance hybrid, in fact, I will let you draw this. Maybe what you should convince yourself is that the resonance hybrid for this molecule is going to be this structure. That's the resonance hybrid for this molecule. No charges. Oxygen has two lone pairs and electron density spread throughout. Okay, so that will be the resonance hybrid. So those were two examples from the homework, and hopefully these would help you as you go through homework problems and practice those. Okay? Bye.